Okay, more with section 6.2. We're now looking at trees. Trees have to be a connected graph that has no circuits. So those are the two things that you must have in order to have a tree. So we're going to choose a graph that is a tree. Well, of course we know that this is not a tree because there are multiple circuits, but just to choose one of the circuits, here's one circuit that's in the graph. So that's not a tree. B is disconnected, so it cannot be a tree. C, again, we have a circuit there, that triangle is the circuit, and D is a tree, so D is our tree. So this is a tree, no circuits, and it's connected. This is a tree, no circuits, and it's connected. But this is not a tree because we have this dark part that is a circuit. A spanning tree. Well, tree says that it is connected, and no circuits. Spanning means that it covers everything. It goes to all the points. So these are spanning trees. This is our original graph, and here's the spanning tree that goes along with that graph. Notice it's connected, it doesn't have any circuits, and it goes to all of the points, or all of the vertices. A minimal spanning tree, what you want to do is you want to start with the smallest weight, so you're going to have the smallest total weight possible. So here's our original graph, and here's two different spanning trees. Now we don't know whether or not these are minimal spanning trees or not, although we do know that since 107 is bigger than 95, that B is definitely not a minimal spanning tree. Well, how we figure out what a spanning tree is, we start by putting in the smallest edges. So 6 is the smallest edge, the next is 10, and we don't want to create any circuits. So far we're okay. If you put in 13, still no circuit. 15, still no circuit. 18, no circuit. 22 will cause a circuit, so we don't put that edge in. And then 33 brings our last point into the graph. So C is our minimal spanning tree. And what we just looked at is Kruskal's algorithm. You start with the points, and then you fill in smallest edge to largest edge, and as long as you don't put a circuit in, you're fine. If you put an edge in that causes a circuit, take that edge back out and go to the next edge. So we want to find a minimal spanning tree for this graph. So what I'm going to do is just put the vertices in. The smallest edge is 1.5, so I put that edge in. The next one is 2.6. 2.6 does not cause a circuit, so we're okay. And then 3.7 does not cause a circuit, so we're fine. Now if you try to put 4.8 in, it causes a circuit. If you try to put 5.9 in, it causes a circuit as well. So this is our minimal cause spanning tree with the edges 1.5, 2.6, and 3.7. So if we want to build a walkways for this college and we want to save money, so we want to have the smallest amount possible and still be able to reach all of the classroom buildings and dorm buildings and so on and so forth. So the smallest is 120, so we're going to put that edge in. Then next smallest, we have 200. Then we have 210. Still no circuit. 220. Still no circuit. If you put in 280, there's a circuit. Actually, we have our minimal cost spanning tree, but I want to show you what happens if you keep on going. If you put in the 280, you have a circuit. Next is 350. If you put in the 350, you have a circuit. If you put in 360, you have a circuit. If you go all the way through to the 500, you're always going to get a circuit past where you have your minimal spanning tree.